Okay, as we've seen, the area of a square forples when the edge length doubles, and there's a very simple reason for that, and the reason is just summarized by this picture. Here we have a square, not a very well drawn square, but and if we double the edge length, we get a square that would be covered by 4 of the smaller squares. So that clearly you have 4 times the area when the smaller square doubles, and that doesn't depend on the size of the smaller square. So anytime you double the edge length, you got to quadruple, or as we say, forple, the area. Now we then construct a graph. Here are edge lengths. Here's the edge length axis marked off, I think, so that this edge length doubles to give this one, and this one doubles to give this one. And here I start with an area here, divide that into half, divide that into half, divide that into half, and divide that into half. So that this is 1/4 of this, this is half of this, this is half of this, so this is 1/4 of this, and this is 1/4 of this. And so using that, we can easily sketch a forpling graph, and you should think how that's going to be done. It probably ought to take 10 seconds and sketch it yourself. Then we're going to label it so that a 1-inch square has an area of 6.3 square centimeters. So here's the graph. I've drawn it fairly carefully, so if you pick any x, like here, and forple that, well, we don't go out that far. Maybe, or double that, I'm sorry, if we double that, we get this. This y value here should be 4 times this y value here, and that seems to work. But of course, we can test that. It's a good way of checking whether we've drawn the graph with some sort of accuracy. Now we want to label a 1-inch square so that it has an area of 6.3 square centimeters. Now I'll talk about why that should be and how that can easily be calculated in your head if you know a little bit of basic information that you don't want to have to rely on Googling to find. Okay, the simple idea that a centimeter is 2.54, an inch is 2.54 centimeters. Now that's basic knowledge. If you square 2.54, you get 6.3. In any case, we can label a 1-inch square that has this area, and then we get a graph that contains the information about how an area in square inches compares to an area in square centimeters. To label the graph, we simply choose any point on the graph, any convenient point. I'm going to choose this point here, and we're going to call this 1 inch, because that's the edge length of a 1-inch square, and we're going to call this coordinate here 6.3 square centimeters. Now we can continue to label this graph. If this is 6.3, then 6 is just a little less than that. So if we're just a little less than double this, so here to here and maybe down just a little bit, now let's say we get 12 centimeters squared. Okay, then if we add another 6, let's say 6 is here, 6.3 is here, we add another 6 and maybe we're here. And now we've got 18 square centimeters. Another such increment would give us 24 square centimeters, and another, might have been a little high with that one, so let's be careful, should give us 30 square centimeters. And down here, here's 1 inch, so if this is 1 inch, then this ought to be about 2 inches. And now if we want to determine the area of, let's say, 1.5 inch square, we can easily do it. So you ought to think about how that would be done. Make sure you understand how the labeling proceeds. Okay, well, now I want to determine what the area of a 1.5 inch square would be. A square 1.5 inches on a side. That's not an easy multiple. That's easy enough. It's 2.24 times the area of a 1 inch square, and we could easily calculate it that way, and you should be able to do that. But if we want to use the graph, at least to illustrate the usefulness of a graph like this for reasonable estimates. We take the 1.5 inches, we come up here and we project over, and we get something between 12 and 18 square centimeters, closer to 12 than to 18. So I would say that the area is maybe 14 square centimeters. It's not 15. 15 would be halfway between. I think 14 is the closest estimate the way I've sketched this graph. But remember, this is a hand-sketched graph. So if I'm really close with 14, it's just dumb luck. I didn't draw the graph all that accurately. But if you calculate it, I think you do come out pretty close to 14 square centimeters for 1.5 inch square. And you can verify that easily enough. Now, of course, you have methods for conversion, but they aren't as geometric as this method. This method is in a lot of ways quite geometric. And this extra picture of what the conversion means and how the conversion goes in the graph that describes the conversion is quite useful. Now, if you can't do that conversion, if you can't figure out, based on the fact that a centimeter is 2.54 inches, and if you don't know that fact, and I've got it just exactly backwards, it's an inch, it's 2.54 centimeters. Let me fix that. Okay, so busy preaching about knowing a few things that I just wrote the units down without thinking. But of course, then I thought about it, and I realized that, well, an inch is bigger than a centimeter, so what I'd written made no sense. An inch is 2.54 centimeters. You should be able to take that using the methods that you've learned in previous courses and figure out that in the first place, 1 inch square should have an area about 6.3 square centimeters, and 1.5 inch square should have an area of about 14 square centimeters. Or use this fact to figure out this fact. And I'll talk about that, but in a separate video. Those are things you should simply know. I don't assume that you really do, because I don't know that that sort of thinking is represented on the SOL. If it isn't, there's a good chance that you haven't seen it except in a very passing manner. And so I will supplement, but not in this video. Okay, so now I want to relabel the graph. So I could say relabel. I could write that as one word because I've got the capital L there. We'll keep it that way. We want to label the graph so that a 0.5 meter by 0.5 meter piece of sidewalk, if a 0.5 meter by 0.5 meter piece of sidewalk weighs 200 pounds, we can use the graph to estimate the weight of a piece that's 0.8 meters by 0.8 meters. This could be a very practical problem. There are other ways to solve it, but unfortunately, the thing that I would expect if I gave this to a typical class is that what people would do is they would set up a proportion, 0.8 meters over 0.5 meters equals X over 200 pounds. And that would give us a completely wrong result. This graph can help us see that that's a completely wrong result and can help us correct that procedure, or can serve as a ballpark estimate. If we're just talking about what do we need in order to handle this bigger piece of concrete, then we can see if it's realistic to try to lift it with, say, 3 or 4 people, or with 2 people, or if you're really strong, with 1 person. I wouldn't recommend it. Okay, so how would we relabel it? Well, 0.5 meters is the edge length of a square piece. So I'm going to label 0.5 meters. Yeah, I think I can label that here. And that labeling is a little small, and the chalk is a little imprecise, but hopefully you can read that, 0.5 meters. And I'll label this point over here as 200 pounds. Okay, now I want to go up to 0.8 meters by 0.8 meters, so I'm going to go to 0.8 meters. Now if this is 0.5, then this would be 10, and 0.8 would probably be about here. Okay, so I'm going to call that 0.8 meters. Don't have a good place to label it down here. Should have been a little more careful. But there's my 0.8 meters, and if I go up to the graph, add across, of course I can scale the graph. If this is 200 pounds, then 400 is probably about here. 600 would probably be about here. I'm not going to label those numbers, but remember that's 400, that's 600. So this looks like it might be 450, 500 pounds. Okay, so don't have room to label that in there, but we can see by pointing that and by understanding what these labelings mean that we probably get something between 400 and 500 pounds, maybe 500 pounds. A more accurate forpling graph and a more careful scaling of the graph could, of course, give us an even better result. But let's just see. Let's say that's about 500 pounds. Actually, it's not 500. That would be 450 or so. And let's check that out in a separate video and address a couple of the issues that arose in this one.